What I want to do next now is actually to show you how we derive, when y equal x beta, okay, plus hero. Okay, so I actually want to show you how we derive that, this is going to be that, okay? So that is what I actually want to derive now. Of course, I've given you the specification of Y matrix, the design matrix S, the beta, and the error. So what I want to show right now is to be able to show how um, the beta cap equal to that. Okay, so when you take a look at this, it's equation one. So that is the specification of a linear model in matrix form. And of course, you know, what is the error? The error there is actually going to be y minus x beta. Okay. Now, if I find the transpose of that, I'm actually going to have this guy. Okay. Now, having this guy, now, if I want to get what I call sum of square error, okay, the sum of square error in a scalar form was actually it's actually going to be this guy here. Okay, so but in a matrix form, it's going to be E transpose E. Okay, it's going to be E transpose E. Okay, so what I gonna do now, I'm actually gonna write Y X beta. Okay, transpose. Okay, and Y minus X beta. Okay, I just wanted to take a look at that. So this is what I call my sum of square error. Okay, in matrix form. So what do we normally do to sum of square error? So maybe I'm going to call this guy equation 2 now. Okay, so what we're going to do to sum of square error is to minimize that. Okay, don't forget, the sum of square error is actually the total unexplained variation. Okay, so the only way we can minimize this, we actually seeking the optimal value of beta. Okay, and if we're seeking for the optimal values of beta, we're actually going to use an approach that will, that will drastically lead to reduction in the sum of square error. So because of that, I'm actually going to differentiate that. Okay, so if I want to, I'm actually going to write, the sum of square error, okay, the beta, okay, the beta here is actually a vector of parameters. Okay, so I want to differentiate this guy. But why can't we do this first? Before we can differentiate, can we expand that? This is going to be y transpose y minus y transpose x beta, okay, minus x beta transpose y plus x beta transpose x beta, when you're trying to multiply out. Okay, maybe we can see simplify further because when you simplify, your differentiation will be very easy to undertake. So I'm actually going to have y transpose y minus y transpose x beta. Okay, so when you use the law of matrix here, I'm actually going to have beta transpose S transpose Y, then plus, beta transpose S transpose X beta. Okay, so when you take a look at that, this can be proved to be the same as that. Okay, so if that is proved to be the same as that, so I'm just going to have sum of square error equal y transpose y, okay, minus 2, okay, beta transpose S transpose y, okay, plus beta transpose S transpose X beta. Okay, now it's time for me to differentiate now because we've been able to simplify, to the lowest time. So differentiation will be very easy to me. So I'm actually going to have the derivative of sum of square error with respect to beta now. Okay, of course, 0 there. So I'm actually going to have beta transpose S transpose Y. okay, plus, okay, the beta transpose beta is more or less like a 2 beta, so I'm actually gonna write 2s transpose x beta. Okay, so when I do that, so I'm actually oh, give me 1 second. Differentiating that guy. I want differentiating that guy should be 2 because S transpose Y because we're differentiating with respect to beta. So when you set that to 0, okay, set that to 0 now, and you cancel out 2. I'm actually gonna have S transpose X beta equal S transpose Y. So what am I gonna do? So I'm actually gonna pre-multiply, okay, pre-multiply by, because I'm looking for beta, so I'm actually looking for something that will make S transpose S identity. So and it's going to be inverse of that. So what I'm going to have now, so I'm going to pre-multiply by that. Okay, I'm going to pre-multiply by that. So equal this guy now. Can you see that? Now this guy is going to be identity. And identity is actually equal S transpose X inverse S transpose Y. And identity multiplied by beta is actually going to be beta. Okay, so finally, that was how we can put a cap on that. So that was how we got S transpose X inverse S transpose Y. Okay, so that is the required proof. Okay, that is a proof that we actually uh, want to figure out. Now, if we have a beta curve like this, we got an estimator. I think the next thing is for us to be able to obtain the mean and the variance of the estimator. Of course, I need to force, obtaining the mean is to see whether the expected value of a beta curve, okay, is actually going to be equal to beta. Now, when that happens, we're trying to say all the parameters involved are simultaneously unbiased estimator. And the moment they are unbiased estimator, of course, we actually, if we want to investigate how reliable it is, so we're going to derive the variance. Okay, so I'm gonna clean my board. Okay, so I'm gonna clear my whiteboard. Okay, so we've been able to prove that that guy, the beta curve, is gonna be S transpose X inverse S transpose Y. So what we want to do now, we actually want to investigate the properties of the properties of that estimator, okay, of the least square, okay, because it's least squared, okay, least squared estimator, okay, the least square estimator of beta curve. Now don't forget the beta curve. So I'm going to tell you this expected value of a beta curve is actually equal to beta because the beta curve is a random variable. If 1,000 investigators should actually study go to the same population, draw sample size randomly, and they draw the same sample size, they're actually going to have different values, for that. So because of that, we can find the mean or the average of that to see whether it's going to give us the true values of the parameters. Okay, and it's that's going to happen. Then number two, I also want to show that the variance of a beta curve that we also call the expansion matrix. The expansion matrix because it's going to be, we're going to have variance covariance matrix. So we also want to prove that it is sigma squared S transpose X inverse. Okay, so we want to prove this too. Okay, let's get started. Okay, so if you want to get started now, so let's see, before of us want to start, uh, investigating the property, the unbiasedness property of a beta curve. So now we know that beta curve is actually S transpose X inverse S transpose Y. When I take the expectation of both sides, what is going to happen? Okay, so expectation into S transpose X inverse S transpose Y. Okay. Now, when you are talking about linear regression relationship, the assumption is that y is a random variable. Anything other than y is actually going to be fixed. So what am I talking about? What I'm talking about is that, everything there is actually is fixed. So, it's more or less like a constant. So it's going to come out, okay? And when it come out, expectation is actually going to grab y because y is a random variable. And recall from a specification of the model, if y equal to this, recall that the expected value of y will be equal s beta because expected value of error is assumed to be equal to 0. So here now, I'm actually going to plug in this guy. So what I'm going to have right now, so I'm actually going to have this guy equal S transpose X inverse S transpose. Then I'm going to plug in X beta. Now let's take a look at this now. Okay, that's going to be identity, right? Identity beta. So which is going to be beta. So what is the implication of what we have right now? The implication of what we have right now is the convergence of, of our estimator to the true value of parameter. That's what it means. So, and that actually makes our beta cap to be unbiased. Okay. Okay. Now that is how we do it. Not in the sense to derive the variance. Okay, because this is an unbiased estimator, I'm actually going to derive the variance. If it is a biased estimator, I'm actually going to need more than variance. I'm going to, I'm actually, I will need a square error. But right now, because this is unbiased, so getting we need to get the variance. Okay, so I'm going to stop my share. I'm going to share my whiteboard again. Okay, so we know that the B cap equal S transpose X, right? S transpose Y. Okay, that's an inverse, right? I want to figure out the variance of a beta cap. So which is going to be the variance of S transpose S inverse S transpose Y. Okay, now when you take a look at this guy here, anything other than Y is going to be called constant, right? Do you know I can let uh, maybe something transpose to be S transpose X inverse S transpose? I'm actually considering M transpose because in the expression, one of the, X actually has a transpose. Now, what is going to be M? If I want to find my M, of course, it's going to be transpose of a transpose, right? So which means I'm actually going to have, taking the transpose of this guy here. Okay, so taking the transpose right now. Okay, so that's going to be X. Uh, the inverse is going to change the position, but transpose doesn't act on inverse other than changing the position. So if I want to write the variance of a beta cap now, I'm actually going to have variance, okay? Now, M transpose Y that I can rewrite as M transpose variance of Y M. Look at that. Okay, I can write it that way. So if I can write it that way, the next thing I'm actually going to do um, is, I think I want to clear my whiteboard now so I can have room. Okay, to clear my whiteboard. So what I'm going to do, so the variance of a beta cap now is actually going to be right here. What is the M transpose? The M transpose is actually here, right? So I'm going to write S transpose S inverse. Okay, S transpose. Then the variance of Y. Okay, the variance of Y. Then what about M? The M that I derived the other time, right? So they're going to be X, S transpose X inverse. Okay, now that is what we have at the moment. The moment I got this guy now. Okay, the moment I got this guy now. So the next thing I'm actually going to do is if y equal x beta plus the error, okay, we got assumption. Assumption is that the expected value of y equal x beta and the variance of y should be sigma square identity. Okay, so right here now, okay, so I'm actually gonna have this S transpose sigma square identity, okay, X S S transpose S transpose X inverse. Okay, and this is a constant variance. Okay, we know sigma square identity is going to be sigma, so I can bring it out. When I bring it out, I'm actually going to have this raised to power this S transpose this S transpose X inverse. Now, when you take a look at these two now, that's going to be identity, right? I'm actually going to have sigma square I, okay, S transpose X inverse. Okay, finally, of course, I'm actually going to have sigma squared S transpose X inverse. Anywhere in the world, that is the expansion matrix of a beta curve, which we also call variance covariance of a beta curve. You know, this is very, very crucial because in statistical analysis, for me to be able to construct a confidence interval on the parameters, okay, linear regression parameters, I actually need this, I need this. Or whether I want to test hypothesis testing or I want to construct confidence interval is very, very crucial. Okay, so that's how we do it.